So that's why you want a dimension of highest variance. Now it turns out that there is an interesting relation between the dimension of the highest variance and the covariance of our data. So let's refresh what the covariance is. I have my data set right there. It's two-dimensional data set, two attributes, x1 and x2. Ignore the colors and the vectors for now. We're going to need them later. So that's the data set. The first thing that we're going to do is we're going to move the data set so that the center is at 0. The way we're going to do that is for every attribute, we're going to subtract the mean value of that attribute, mu of a, from every instance, right? So instance I, attribute A, I'm going to subtract the mean of attribute A. What this means is that the overall mean of the data is going to be exactly at 0. And we do that because it's going to make the math a lot simpler on all the subsequent slides. So the 0 is, the 0 coordinate is exactly in the center of the data. This makes it very easy to express the covariance matrix of our data. So a covariance matrix, it's going to be a 2x2 little matrix with numbers like that. And remember what the numbers mean. The first number in the upper left corner, the 2, that's the spread of the data along the first attribute x1, right? So that's how much it varies if you just looked at the x1 coordinate of these points. So you get a 2, and that agrees with your intuition. The data is pretty spread out along the x dimension. 0.6 is the spread along the x2 attribute, right? And you get a smaller number because the data isn't nearly as spread out around the x2. And the two numbers off diagonal, they happen to be identical. It's the covariance of the first and the second attribute. And the way you compute the covariance is you look at the value of attribute 1 and the value of attribute 2 in some instance I, you multiply them together and you add it up over all instances. Now that's not usually how we compute the covariance. Usually you subtract the means, right? But this time what we did is we centered the data so all the means are 0. So we can write it out as just a product of two scalars, because the means are 0. Right. So that's how you compute the covariance. Now what does it mean? The way to interpret the covariance is how one attribute changes as the other one changes. So basically, as I increase x1, as I increase or decrease x1 by a certain amount, how is x2 going to increase or decrease? So as I, maybe as I add a unit to x1, how much do you add to x2 as far as the data is concerned? Or another way to think about it is the two attributes, do they sort of increase, are they bigger than 0 and smaller than 0 for the same instances, or do they go in opposite directions? So the color of the points actually represents the two kinds of points. The green points are the ones where you have a positive, where the difference in the first attribute and the difference in the second attribute go in the same direction. Right? So for example, for that point right there, the lowest point, the leftmost point, its x1 coordinate relative to the mean is negative, and x2 is also negative. So you're going to multiply a negative by a negative, it's going to add a positive number to the covariance. For the red points, one attribute is above the mean, another one is below the mean. So for that point, for example, x1 is smaller than 0, x2 is bigger than 0, so you're going to get a negative number in that sum. That will decrease your covariance between attribute 1 and attribute 2. Okay. Great. So that's our covariance matrix, and of course you have the variances on the diagonal. Now, it turns out that the covariance matrix does pretty interesting things when you take it and start multiplying random vectors by that matrix. So suppose I pick some vector in that space, and I'm picking this red vector, which has coordinates -1, 1. So let's see what happens if I take that vector and I multiply it by the covariance matrix. Okay. So here's my covariance matrix. I multiply it by the vector -1, 1. What I get out is -1.2 minus 0.2. Right? It's pretty easy to see. You're just -2 plus 0.8. It's -1.2 and so on. Okay. So I get a new vector, and that vector is different. So we can plot that vector. Great. That's what it looks like. That's the result of the product. Now suppose I do it again. I take this new vector, the one that points minus 1.2, minus 0.2, that one, and I multiply it again by the covariance matrix. Well, I get another vector. It's minus 2.5, minus 1.0, and if I plot that, that's what it looks like. Okay? So what seems to be happening is, as I multiply by the covariance matrix, the vector is getting longer, and it's also turning. It's turning counterclockwise. Okay, so let's do it again. I'm going to take it, multiply it once again by the covariance matrix, and I get minus 6, minus 2.7. And if I plot that, my intuition breaks down. Whoa, right? It has gotten longer, but it's no longer turning. Right? It seems to, so it's still turning, but it's turning by a smaller and smaller angle each time. Okay, so let's do it a couple more times. I multiply it again and again. I get these new vectors, and up with minus 33, minus 15. I can't plot them anymore. They're way there beyond the floor. But I can look at what direction they're pointing at, right? I can look at the slope. And to look at the slope, I just take the second component and divide it by the first component. So what is the slope of that line? And what I see is that the slope is actually converging to some value, 0.45. And that value, that slope, happens to be the slope of that little blue vector E2 that I have there. And that vector also happens to lie along the direction of the greatest variance in my data. That's the direction along which the data seems to be spread out the most. So at this point, we're just making an observation. We're going to prove it later. But for now, just notice that as you multiply a vector by a covariance matrix, it seems to be turning towards this dimension where the data is spread out maximally. Right, where the data points are spread out the most. Now, another thing that's interesting is, as I keep multiplying it by the covariance matrix, after a certain number of iterations, it's not going to be turning anymore. Once it's pointing along this dimension of the greatest variance, it's just going to get longer and longer and longer, but it's not going to turn. And in linear algebra, there is a name for such vectors. They're called eigenvectors. They're eigenvectors that they have the property that when you multiply them by a matrix, they don't change. They change by a scalar. So they become shorter or they become longer, but they don't turn at all. That's the definition of an eigenvector. And the scaling factor, how much longer or shorter they become, that's known as an eigenvalue. So it basically tells you, is it going to be growing or shrinking as you multiply. So the principal components in PCA are just eigenvectors with the largest eigenvalues. I'm stating it for now, but what we're going to do is we're going to prove why that is actually the case. And there are some interesting properties of eigenvalues and eigenvectors.